This is lesson 8.4, add, subtract, and multiply radical expressions. Our learning objectives are to add and subtract radical expressions, multiply radical expressions, and use polynomial multiplication to multiply radical expressions. Little reminder for you, we're dealing with radicals in this chapter 8. And so radicals have an index value. That's the type of root. Like a square root has an invisible 2, a cube root has a 3, a fourth root has a 4, etc. The value inside of the radical is called the radicand. And then, you're used to calling this a square root, but it's actually the symbol used for many kinds of roots. Not just square roots, but cube roots, fourth roots. And this symbol is called the radical symbol because calling a root a radical, that's the cool way that we do it. That's cool to call a root a radical instead of vice versa. Now, to add and subtract radical expressions, we have to know this definition of like radicals. We know about like terms that like terms can be combined together, right, to simplify. And the same thing happens with radicals. Like radicals are radical expressions with the same index and the same radicand. All right, so if they have the same index value and the same radicand, then radicals can be added together or subtracted as like terms. They're called like radicals. So let's practice this concept so you get comfortable with it, and it's really cool. Like you're gonna realize, wait, I didn't know I could do that, and it's kind of cool. So here's example 8.36. We're gonna jump straight into it. When I see 2 root 2 minus 7 root 2, that's equal to negative 5 root 2, because 2 minus 7 is negative 5. And these were like radicals. We can only do this if the radicals have the same index. In this case, the index is invisible. It's 2. And the same radicand. Yeah, the radicand in both cases is 2. This is why we can do it. It's kind of like the same idea as if you took 2x and subtracted 7x. They're like terms, so you're used to this. 2x minus 7x, that's negative 5x. All right, so just in the same way we can do this, we can also do it like this. Let's try some more. Okay, what if we see 5 times the cube root of y plus 4 times the cube root of y? Well, these radicals have the same index of 3 and the same radicand of y, so they are like radicals. And so we can add them together. 5 plus 4 is 9. And that's why I can say that this simplifies to 9 times the cube root of y. Let's try it again. And here we see 7 times the fourth root of x minus 2 times the fourth root of y. And I stop and I think, wait a second. Hey, we have the same index value, but we don't have the same radicand. So these are not like radicals. They cannot be combined together. And so this is as far as it simplifies. It doesn't simplify any further than the original statement. Okay, that's as far as it goes. I'm done. Let's practice some more. Sometimes instead of, adding 2 terms together, right, like we did here and here and here and here, we had 2 terms. Well, what if I have 3 terms that have like radicals? So here's 2 times the square root of 5 times n minus 6 times the square root of 5 times n plus 4 times the square root of 5 times n. And we see that we've got the same radical index value. I'm just going to make those invisible 2's appear, right? The index is 2, it's invisible. And the same radicand, 5n, 5n, 5n. Okay, so these are like radicals. Therefore, I can take 2 minus 6 plus 4. Well, that's negative 4 plus 4, which is 0, times the square root of 5 times n. But 0 times anything is 0, so that's my final answer. Great. Let's try this next one. The fourth root of 3 times x times y plus 5 times the fourth root of 3 times x times y minus 4 times the fourth root of 3 times x times y. Question, do I have the same index value for all the radicals? Yes, 4, 4, and 4. Do I have the same radicand for all of the radicals? Yes, 3xy. So I can take this, I'll make this one invisible. It's invisible, but I'll make it visible. This is 1/4 root of 3xy, right? This is one of them. So I'll put the coefficient 1 in front, so it'll help you see that I'm taking 1 plus 5, which is 6, minus 4, which is 2, and I get the coefficient of 2 multiplied in front of the 4th root of 3 times x times y, and that's the answer. I have combined like radicals. All right, so let's go ahead and move forward to example 8.38. And I see the square root of 20 plus 3 root 5. Currently, I don't have the same radicand, so I can't combine these together currently in the way that it currently is. But we learned last time how to simplify square roots. Okay, what we're going to do is we're going to take this square root, if it can be simplified, and we're going to use the product rule to turn it into 2 square roots. And we put the perfect square in the first one, and we put the leftovers in the second one. So when I look at 20, I realize, wait, 20 is 4 times 5. And 4 is a perfect square, so it can go in the perfect square radical. And 5 is the leftovers. It's not a perfect square. It goes in the second radical. And so I've turned the square root of 20 into the square root of 4 times the square root of 5 using the product rule of radicals. And the square root of 4 is 2. Okay, so I rewrite the square root of 4 as 2, and then I multiply it by the square root of 5. And then I still had this other piece, this plus 3 root 5. So I'm going to include that in my expression again. Great. So this, what I started with, is equal to this. And I now see that I have same index and same radicand for these radicals, so I can combine them as like terms. So 2 root 5 plus 3 root 5 is 5 root 5. That's my answer, 5 times the square root of 5. All right, let's look at this next one. The cube root of 24 minus the cube root of 375. I currently have the same index, but I don't have the same radicand. And so what I'll do is I'm going to break each one of these into pieces. Okay, so I'm going to use the product rule for the first cube root. Okay, so I'll figure out what that stuff will be. And then I'm going to use the product rule again for the second cube root. And my goal, since the index is 3, it's to think of perfect cubes. And 24, I can think of a perfect cube of 8, which multiplies with 3 to make 24. Right? 8 times 3 is 24. I just used the product rule, putting a perfect cube in the first radical and the leftovers in the second radical. Now I move on to 375, and I think in my brain, well, I know a perfect cube that 375 is a multiple of. It's 125, right? The cube root of 125, it's 5. So yeah, 125 is a perfect cube, and if I multiply that by 3, then 125 times 3 is what gives me that 375. And I think your brain is clever. I think your brains are very clever. You just have to remember your perfect squares and your perfect cubes, right? You have to have these kind of in your mind. So when I see 375, my brain says, hey, take 125 and multiply it by 3. I think you're going to get better and better at this as we go. All right, so the cube root of 8, it's 2. And so I get 2 multiplied with the cube root of 3. And now I'm subtracting the cube root of 125, which cleans up to 5, which is multiplied with the cube root of 3, right, the leftovers. And so now I notice I have 2 cube root of 3 minus 5 cube root of 3. I've got the same index and radicand for these two radicals, That means they're like radicals. So I take 2 minus 5, which gives me negative 3, and I multiply that by the like radical of cube root of 3. Lots of 3's in my answer. Negative 3 times the cube root of 3. I love it. Okay, well, let's take things further. So I'm going to give you two expressions in this example 8.39 that we're going to simplify. That's our goal. We're going to simplify these babies. Okay, let's jump in. So when I see this square root 50m squared, I'm going to break it into two square roots. I'll show you. So I have this 9 in front, but I'm going to create the perfect square root and the leftovers square root. And then I have this minus 6. And for this square root, I'm going to do the same thing. I'll have the perfect square root times the leftovers square root. And 50, I can think of a perfect square that multiplies with another number to make 50. It's 25 and 5. And 2. 25 times 2 is 50. So this is what I'm doing. Okay, and now I see this m squared. Well, that is a perfect square. M squared is a perfect square, so I put it in the perfect square radical. Now moving on, let's look at this radical. 48. Can you think of a perfect square that multiplies with a number to make 48? And you think for a second, and yeah, you found 16 and 3. 16 times 3 is 48, where 16 is a perfect square and 3 is the leftovers. And then I see this m squared, which is a perfect square already, so I'll put m squared right there. Okay, so now I'm going to clean this up even further, and I'm going to say that this is equal to 9 times, well, the square root of 25, which is 5, times the square root of m squared, which is m, times the square root of 2, minus 6, times the square root of 16, which is 4, times the square root of m squared, which is m, times the square root of 3. All right, and now I see, well, I could simplify this a little bit. 9 times 5 is 45, times m, times the square root of 2, minus, well, 6 times 4 is 24, times m, times the square root of 3. Great. So we get to this point, and I ask the question, can this be simplified any further? So I look to see if the radicals are like radicals. Well, they have the same index value because they're both square roots, but one has a radicand of 2 and one has a radicand of 3. These are not like radicals. I cannot simplify any further. This is my final answer. All right, let's try another. Here's the cube root of 54 times n to the fifth minus the cube root of 16 times n to the fifth. What I'm going to do is I'm going to use the product rule of radicals. So I'm going to create a perfect cube root and the leftover cube root minus another perfect cube root times the leftover cube root. Okay, so here's the index value of 3. It's a cube root in all the cases. And I need to think of a perfect cube that multiplies with a number to make 54. And I found it. It's 27 times 2. 27 is a perfect cube of 3. And if I multiply it with 2, it makes 54. Now I look at n to the fifth power and I say, well, I need a perfect cube. So I'm only going to multiply 3 n's together. I'm going to take n cubed, which means that this leftovers has n squared, right? Because n cubed times n squared is n to the fifth. I now have my perfect cubes in the first cube root and the leftovers. Let's do the same thing with this radical. So the cube root, well, I've got 16, and I can think of a perfect cube that multiplies with a number to make 16. 8 is a perfect cube, and if I multiply it with 2, it makes 16. And then same deal, I have n to the fifth again, right? Same as before. So I'll put 3 of those n's multiplied together in the first cube root, and then the remaining n's in the second. So there we go. Now we can simplify this and this because these are the perfect cube roots. The cube root of 27 is 3. The cube root of n cubed is n. And then I'm going to multiply on the leftovers. And now I subtract the cube root of 8, which is 2, times the cube root of n cubed, which is n. And then I multiply on the leftovers. And now I look and I ask myself, are these like radicals that I have remaining here? Yes, they have the same index and they have the same radicand. So I'm going to take 3n and subtract 2n, and I get 1n. 3n minus 2n is 1n. And multiply that by the cube root of 2n squared. That is my final answer, simplified all the way. All right. So zooming out, that's what we've accomplished so far. And we're ready to move forward and talk about the product property of roots. Okay, so the product property of roots we've already discussed in section 8.2. It says that if we have the nth root of a times b, it's equal to the nth root of a times the nth root of b. Okay, so if I have the product of two things inside of a radical, I can separate those things and put them in their own radicals. Yeah, the index of the radical has to be the same. Now, we could go in this direction from a single radical to two radicals, or the other way. So I've written this the other way, right? So we can go from two radicals into a single radical, like that. You could do this anytime you want to. That's the product property of roots, and it's useful as we simplify roots. Okay, so let's look at example 8.40 right here, and I'm going to zoom in. And this example says multiply, okay, 6 times the square root of 2 times 3 times the square root of 10. And the cool thing is we can just take these numerical values, 6 and 3, and multiply them together, right? And, maybe we reorder things. So I'll reorder it so you see it clearly. Multiplication is commutative, meaning we can write it in any order that we want to. So I'm going to write it like this. I have 6 times 3 times the square root of 2 times the square root of 10. And I've grouped 6 and 3 together so I can multiply them. Their product is 18. And then I've grouped the radicals together, 2 and 10, and I can write them as the square root of 2 times 10, which is the square root of 20. Let me see if I can get a good square root. There we go, square root of 20. All right, now we ask a question. Can I take the square root of 20 and simplify it, right? So I'm going to break this back apart a little bit because the square root of 20 is the square root of 4 times the square root of 5. Right? 20 is not just 2 times 10, but it's 4 times 5. And the reason why I've split this apart again is because 4 is a perfect square, right? So I got my square root, that's a perfect square, and I got my leftovers. And so I now can turn the square root of 4 into 2 in my brain, right? Square root of 4 is 2, so 18 times 2, that is 36, and then that's multiplied by the square root of 5. Great. Little recap. When I see 6 times the square root of 2 times 3 times the square root of 10, multiplication is commutative. I can organize things how I want to. I put 6 first, then 3, then the square root of 2, then the square root of 10. And 6 times 3 is 18. And the square root of 2 times the square root of 10, well, that's the square root of 2 times 10, which is 20. Then, man, I want to break this 20 back apart. Is there a perfect square that multiplies with another number to make 20? All right, well, let's use the product property and put 4 as the perfect square in the first root and the leftover 5 in the second root. And now the square root of 4 is 2, so 18 times 2 is 36, and now I multiply that with root 5. All right, there we go. Let's try another, and this time let's play with negatives a little bit. Well, this one's pretty easy because a negative times a negative is a positive. And so you could immediately just make those both positive. Negative times a negative is a positive. Negatives are gone. Don't even worry about them in this case. And let's go ahead and take 5 and multiply it with 4, and multiply that with the cube root of 4, and multiply that with the cube root of 6. What I did was I reorganized all of my products, right? So all of my factors of all this multiplication that I have, 5 times 4 times cube root of 4 times cube root of 6. And 5 times 4 is 20. And I can use the product rule that we just discussed above, right? The product rule says that I can take two radicals and combine them into a single radical, multiplying their radicands together. As long as the index value is the same, I can do this. And so 4 times 6 is 24. Okay, now I'm going to see, can I break this thing back apart again, right? Like this. Can I break it into pieces where I have a perfect cube and the leftovers? And yes, I can, because the cube root of 24 can break down into the cube root of 8, which is a perfect cube, times the cube root of 3, which is the leftovers. And the cube root of 8 is 2, all right? Cube root of 8 is 2, because 2 cubed is 8. And so 20 times 2 is 40. I'm going to multiply them together. And then I have the leftovers, which is the cube root of 3. Great, let's go ahead and move forward in this lesson. And so let's try this process again. We're just getting more and more comfortable with this. And so maybe you decide to reorganize all of your factors, like 10 times 4 times the square root of 6p cubed times the square root of 3p. So I've reorganized everything. And so now it'll make sense why I'm taking 10 times 4 to make 40. And I'm going to use the product property to combine these two square roots into a single square root, multiplying their stuff together. Now, 6 times 3, that's 18. And p cubed times p is p to the 4th. Like this. And at this point, I'm going to use the product property again of radicals, breaking the radical that I have into two separate radicals. One will have all the perfect squares, and one will have the leftovers. Okay, so 18, it's a number that is a multiple of a perfect square, of 9. 9 times 2 is 18, right? So 9 is a perfect square. And if I multiply it by 2, it gives me 18. And then p to the 4th is a perfect square as well, because that the exponent of 4 is a multiple of the index, which is invisible. It's 2, right? The invisible index of 2. I'll make it invisible again. Great. And so now I can write my final answer. Okay, and by the way, the square root of 9 is 3. I'm going to take the square root of 9, 3, and multiply it with 40 to get 120. And then the square root of p to the 4th is p squared. And then I have my leftovers. There they are. All right. Well, let's try one more like this. And I'll move this just a little bit out of the way. Great. So when I see 2 times the 4th root of 20y squared times 3 times the 4th root of 28y cubed, I will immediately reorganize. So I'm going to multiply 2 times 3 times the 4th root of 20y squared times the 4th root of 28y cubed. Okay, now multiplying 2 times 3, getting 6. And then using the product rule to combine two radicals into one single radical with the same index, yeah, 4th roots, I can multiply 20 times 28. And 20 times 28, well, that's 280 times 2. That's going to be 560. And y squared times y cubed, that's going to give me y to the fifth. All right, why did I just combine all this together? So that I can break it all apart again. All right, so I'm going to now take 560 and split it into a perfect fourth, right? Because the index is 4, so we're thinking a perfect fourths, okay, times the leftovers, right? So I'm splitting this radical back into two radicals using the product rule, product property. And the fourth root that I can think of, well, the fourth power would be 16. Okay, the perfect fourth of 16. If I multiply it with 35, that's what will give me 560. 16 times 35 is 560. Great. At this point, I think y to the fifth, well, I need to break y to the fifth into y to the fourth for the perfect fourth, and then y for the leftovers. Okay, y to the fourth times y is y to the fifth. And lastly, let's go ahead and clean things up for our final answer. Well, the fourth root of 16 is 2, so I'm going to take that result and multiply with 6. 2 times 6 is 12. That's why I have 12 here. And then the fourth root of y to the fourth is just y. And now I'm going to multiply on my leftovers. The square root of 35 times y. Those are my leftovers. It doesn't clean up any further than that. It's my final answer. Great. So now let's practice multiplying expressions with radicals as if they're polynomials. Okay, so we're going to use polynomial multiplication concepts to multiply radical expressions. And you're going to see it like works the same as if I'm multiplying polynomials. So when I see the square root of 6 times the square root of 2 plus the square root of 18, I'm going to think of distribution of the square root of 6 into both of these terms. Okay, and I can go ahead and use the product property to combine the radicals together immediately. Like I can say the square root of 6 times the square root of 2 is equal to the square root of 6 times 2, 12. Okay, and then I can add on the square root of 18 times 6, right? So the square root of 6 times the square root of 18 is literally the square root of 6 times 18. I can just write it like that for now. Okay, so I get to this point, and well, 6 times 18, like I can make it bigger, or I can think of like 18 breaks down, right? So I can write 18 as 6 times 3. And then 12 also breaks down into like prime factors. So you could think of 12 as 2 times 3 times 3. No, 2 times 3 times 2. That's going to be the answer right there, right? 12 is 2 times 2, which is 4, times 3 makes 12. Why did I do this? Because now I can see that I've got these two 6's under a square root, right? And so if you have two of the same factor inside of a square root and everything's multiplication, well, the square root of 6 times 6, right? 6 times 6 is 36. The square root of 36 is 6. So I can pull that out, and I can have 6 root 3. And then in this case, well, I have 2 times 2, which is 4, and the square root of 4, that's 2. So here I get 2 root 3. And then I see that I have the same radicals, right? The same index values with the same radicand. So these are like radicals. So I could say that 2 root 3 plus 6 root 3 is 8 root 3. And I have simplified fully. Sometimes it helps to take numbers and break them into the prime factors to see how you can, break things down all the way. Let's look at the next one. The cube root of 9 times 5 minus the cube root of 18. We're going to distribute. And so I'll just write what I have. I have 5 times the cube root of 9. Right? I just multiplied them together, 5 times the cube root of 9. Now, minus the cube root of 9 times the cube root of 18. So I'll immediately use the product rule and say that's the cube root of 9 times 18. So I'm combining the two radicals into a single radical with the product rule. And now maybe I break this stuff up a little bit further because, 9 is 3 times 3 and 18 is 2 times 3 times 3. Right? So let me show it to you. So 9 is 3 times 3. And then 18, I'm going to find its pieces, right? Which are 3 times 6. And 6 is 2 times 3. Maybe I just leave it as 6. Because I have just discovered that I have 3 of the same value factors under a cube root. Okay? And so it'll make sense that I'm going to say this is equal to 5 times the cube root of 9 minus 3 times the cube root of 6. Because I had the same factor repeated 3 times under a cube root, right? This is 3 cubed, so the cube root of 3 cubed is 3. But the 6, it got stuck under the cube root. It's not allowed to escape. And so now I have my final answer. All right. Let's try multiplying expressions with radicals in them with thinking of them as binomials, polynomials. So when we multiply a binomial times a binomial, we FOIL. And that's what we're going to do in this case. Again, we're going to FOIL, first, outer, inner, and last terms, just like we did back in the day. All right, so let's multiply the first terms together. 3 times 4, right? First terms of each binomial. 3 times 4, that's 12. And now I'm going to multiply 3 times negative 2 root 7. And I get negative 6 root 7. Right, just think of what 3 times negative 2 is. That's negative 6. And then we still have that root 7. Now let's multiply the inner terms together. 4 times negative 2 root 7. And that gives me negative 8 root 7. And then last terms. Negative 2 root 7 times negative 2 root 7. That's positive 4. Right? Because negative 2 times negative 2 is positive 4. And then root 7 times root 7 is 7. Now, maybe I tell you something really fast. I'll put it down here in this corner. The square root of anything, okay, like a smiley face, square root of a smiley face times the square root of a smiley face equals a smiley face. This is a great rule to remember. The square root of anything times the square root of anything is just that thing. So now I'll replace smiley faces with 7s. The question is, the square root of 7 times the square root of 7, what does it equal? Well, it equals 7. Okay? So the square root of 7 times the square root of 7 is 7. And so now we got to this point. And maybe I say 4 times 7, well, that's 28. I'm going to replace 4 times 7 with its value, 28. And now I'll combine like terms. 12 plus 28 can be combined together as constants, and 12 plus 28 is 40. And then I notice that these terms have like radicals. They have the same index with the same radicand. And so negative 6 root 7s minus 8 root 7s is negative 14 root 7s. And I now have my result. This is as far as it cleans up. I've simplified as far as I can. Let's try this again, but maybe we play with cube roots instead of square roots. Here we played with square roots. Let's play with cube roots a little bit. And so same idea, I'm going to FOIL. First terms, outer terms, inner terms, and last terms multiplied together because these are two binomials. And the cube root of x times the cube root of x. Well, that gives me the cube root of x squared, right? I'm using the product rule. I'm just taking x times x and putting them inside of the same cube root. Okay, moving forward, now that I've multiplied the first terms together, I'm going to multiply the outer terms together. 4 times the cube root of x. Okay, so I'll put a plus 4 times the cube root of x. Now I'll multiply the inner terms together. Negative 2 times the cube root of x. And then lastly, I have negative 2 times positive 4. The last terms multiplied together gives me negative 8. So I'm at this point. I ask myself, do I see any like radicals that I can combine together as like terms? And the answer is yes. I see 4 times the cube root of x minus 2 times the cube root of x. These have the same index value with the same radicand. Okay, so 4 minus 2 is positive 2 cube root of x. And then I have the minus 8 at the end. Yeah. Now, I could not combine this as a like radical with these because the radicand was x squared, whereas these were just x. And so this can't be combined with anything else. This is all done. This is all done. We have 3 terms which are not like terms. This is the solution. Moving on. Well, let's go ahead and multiply 2 binomials together. Again, yes, once again, in example 8.44, we're going to FOIL. Okay? But this time, like, we got radicals multiplied with radicals again and again and again. So you'll see how this might look a little more complex, a little more complicated to you. So looking at this, I'm going to multiply the first terms together. 3 root 2 times root 2. And once again, I'm going to say the square root of smiley face times the square root of smiley face is equal to a smiley face. Okay? And then what is the value I'm talking about instead of smiley face? Well, I'm talking about 2. The square root of 2 times the square root of 2, that is equal to 2. All right? So I'm taking the square root of 2 and I'm multiplying it with the square root of 2 to get 2. And then 3 was multiplied in front. So this is 3 times 2. Okay. So moving on, we're now going to look at multiplying the outer terms together. So the outer terms are 3 root 2 and 4 root 5. So let's multiply 3 times 4, and we get 12. And then let's multiply root 2 times root 5, and I'll use the product rule to turn them into root 10. Right? Root 2 times root 5 is root 2 times 5, or root 10. Now let's move on to the inner terms of FOILing, where we'll multiply negative root 5 times root 2, which gives me a negative root 2 times 5, which is 10. Right? So I'm using the product rule again. And then let's move on to the last terms. Negative root 5 times positive 4 root 5. And that gives me a negative 4 times 5. Why am I saying that? Well, root 5 times root 5 is 5. Let me get out the smiley faces. The square root of smiley face times the square root of smiley face is equal to a smiley face. Therefore, the square root of 5 times the square root of 5 is equal to 5. Hopefully this is starting to sink in for you, because this is going to come up multiple times in your assignments. All right, so now that I got to this point, well, I'll multiply 4 times 5 together to get 20. Right, so there you go. 4 times 5 is 20, so I'll replace that there. And I'll also take 3 times 2 and turn it into 6, right? Because 3 times 2. And now I'm going to combine like terms. And I'll say, well, 6 minus 20 is negative 14. And 12 root 10 minus 1 root 10, those are like radicals. 12 root 10 minus 1 root 10 is 11 root 10. And now I have my final answer. I've simplified fully. I would like to take this opportunity to remind you about some of the special products we've talked about in this class. All right? So some special products we've discussed are, this perfect square trinomial, a plus b squared is expanded to a squared plus 2ab plus b squared. This is a perfect square trinomial. It's the perfect square trinomial of a plus b squared. Now, if I had a minus b squared, the perfect square trinomial would be a squared minus 2ab plus b squared. Right? So this binomial, when I square it, becomes that perfect square trinomial with this minus sign, right? This minus sign stays there. If it's a plus sign between the two terms in the binomial, then we get that plus sign. So we've seen these in the past, perfect square trinomials. We learned factoring skills for them. And then a reminder about the product of conjugates. If I take two conjugates, remember a conjugate is where you have the same two values with opposite signs between. Okay? A and B, plus and minus. Well, if you multiply them together, then you get a squared minus b squared. And that's called the difference of squares. So this is the factored version of the difference of squares. These are the factored versions of perfect square trinomials. And why did I just bring that up? Because we're going to see that we can have a binomial with a radical in it squared, right? So this 2 plus root 3 squared reminds me of this special product, a plus b squared. And you could take two different routes to get this done. You could follow this general formula that you know that's also on your formula sheet for tests. Or you could realize that this is a binomial squared, so it's a binomial times itself. So you can multiply 2 plus root 3 by 2 plus root 3 to get what I'm about to get. So one of two ways. I'm just going to use this formula since I know it pretty well. So I'm going to take the first value and square it. The first value, I'm going to square it. In this case, it's 2. I square it. Now I'm going to add 2 times a, which in this case is 2, right? A is 2, times b, which is the square root of 3. And then I'm going to add b squared, right? So I'm moving on to this stuff right here. And b is the square root of 3. So I add the square root of 3 squared. Okay, now I just clean this all up and I say, well, this is 4 plus, 2 times 2, which is 4, multiplied with the square root of 3, plus the square root of 3 squared. Well, the square root of 3 squared is 3. And lastly, I would take 4 plus 3 since they're like terms, and I'll add them together to make 7. So my final answer is 7 plus 4 root 3. Great. All right. Well, what if I had, instead of a plus sign, a minus sign? Well, I would follow this format, okay, for this special product of a binomial squared. And so I would take the a value and square it, and then subtract 2 times a times b, and then add the b value squared. So in this case, the a value is 4, so I take 4 and square it, minus 2 times a, which is 4, times b, which is 2 root 5, and then I'd add b squared, which is 2 root 5 squared. And now I clean it up, right? 4 squared is 16, because 4 times 4 is 16. And then I have here a negative 2 times 4, which is negative 8, but then times another 2, which is negative 16, root 5. And now I add that with 2 squared, which is 4, times root 5 squared, which is 5. And 4 times 5 is 20, so I'm going to replace this with 20. And then clean it up a little further because 20 plus 16 is 36. And I still have this minus 16 root 5. There's my answer. And let me leave you with one more opportunity. We're going to take the product of conjugates, where if I see A plus B times A minus B, right? These are conjugates. And if I multiply them together, it gives me the difference of squares, A squared minus B squared. So if I recognize that, hey, here I have the same two terms, 5, 2 root 3, 5, 2 root 3. And those two terms are separated by opposite signs in each binomial, a negative sign and a positive sign. These are conjugates. And so to use my pattern, I just take A and I square it. So I take 5 squared. And then I subtract B squared. B is, in this case, 2 root 3, and I square that. And so 5 squared is 25. And then I subtract, well, 2 squared, which is 4, times the square root of 3 squared, which is 3. And then, 4 times 3, I turn it into 12. And 25 minus 12, that's 13. This is my answer. I have simplified this thing. This thing right here that we started with is just 13 in disguise. All right, we have completed this lesson, 8.4, and you are getting more comfortable with adding and subtracting and multiplying radicals and finding, like radicals that you can combine together as if they're like terms. I hope this has been helpful. I hope you have a great day, and I'll see you in the next one.